Started. Thanks for joining back. So we have an exciting remaining day with speakers from multiple industry and organizations. So we'll be starting with AWS presentations. It will be presented by Raghunath Raja Chandrasekhar. Raghu is a senior engineer at Amazon Web Services, where he is the technical lead for a team that builds HPC technologies to run applications more efficiently in the cloud. He leads the libfabric development efforts at AWS and also serves as the maintainer for the Elastic Fabric Adapter provider, that is the EFA. And prior to AWS, he was a senior engineer at Cray, conducting research on next generation HPC storage technologies as part of an advanced development group. He received his PhD from the Ohio State University. He has authored more than 20 scientific publications, presented talks at several international venues, and serves on the technical program committees and steering committees of multiple HPC conferences and workshops. So he will be talking today about scaling message passing on Amazon Web Service with Elastic Fabric Adapter. So Raghu, please share your screens and you can get started.
Thank you for that kind introduction, Dr. Panda. Can you hear me okay? And you can see my screen as well?
It's coming up, yes.
Okay. Let me make sure I get the, okay. All right, so let's get started then. So first of all, before I get started, I think it's really good to be back at MUG. I missed a couple of years, but seeing how the conference has evolved over the years has been amazing. Particularly this year, I see an amazing lineup of talks. I look forward to the rest of the sessions. And like someone else mentioned before, it's unfortunate we cannot meet in person. I'm still getting used to the whole presenting virtual conferences thing. Hopefully we all get rid of this pretty soon. So I'm here to talk about scaling message passing on AWS. But I looked through the audience list, so I'm gonna do one of two things, right? I'm gonna step through an overview of the different HPC solutions on AWS, just to give a sense for what the breadth of offerings and how people do HPC on our platform, and then give an overview of EFA and a custom protocol we've designed called SRD. And then again, this is content I've presented before in other venues, but I thought it would be useful to this community. And then I'll give an overview of MAPHX solution for AWS and talk a little bit about the other MPI implementations we support as well. And then dive into some application level case studies. But anytime throughout the talk, feel free to stop me through the moderators or put in your questions in Zoom and I'll get to them. Even if I don't get to them during the talk, I'll make sure I'll respond to all of them after the talk. All right, so and before I dive into the actual solutions that we have, I think one thing I want to make clear is what AWS looks at as metric for success, right? And each vendor looks at it a little differently. The way we look at it as time to results is our key metric for success. And it's not just about running a benchmark and showing you're better or showing a single application and seeing it scales. It's more really about the workflow that you have end to end, right? That's everything from spinning up your cluster to submitting jobs, getting it scheduled right away to getting your results and visualizing it and so on. So if you think of a typical on-prem environment, you're often working with finite capacity. If you're a supercomputing center, you work through the RFP response cycle, you procure a system, you accept it and deploy it. And that in itself takes a while. And you often tend to size for peak, right? You have a sense statistically based on how your users use your system. You have a sense for how big your system needs to be that you procure. And if it's a busy day, if you have a lot of jobs coming in, you're going to sit in the queue for a long time. And if it's the other end of the spectrum, you have resources that are sitting idle and you end up paying capital expenses for that. So really the way we think about it is we want to give you the building blocks that let you spin up resources as you need and only pay for them as you go. So with that as the metric for success, this is a sampling of services that might be of interest to HPC customers. But really at the center of it is the compute capabilities, right? So particularly EC2, which is the Amazon's Elastic Compute Cloud offering. It's optimized for different types of workloads. We have compute optimized instances, kind of like our C series, accelerated instance types with GPUs. For example, we have a P series of instance types that have up to 8 V100 GPUs. We have storage optimized instances with like NVMe, not local NVMe flash. It's kind of all over the place, right? So there are tens of different instance types and over 175 services that kind of work around them. Kind of if you go outside the compute bubble, that you have a bunch of storage, visualization, orchestration tools. For example, I'll call out the Amazon FSx for Lustre service, which is a managed parallel file system as a service, right? So you can click a button and get a Lustre file system at a size that you desire. And that's been working really well for customers. Kind of the other service I want to call out is AWS Parallel Cluster. In reality, it's more than a service. It's a tool that lets you spin up a parallel cluster, HPC system in the cloud, and gives you a very familiar kind of interface to a system if you're coming from the on-prem world, right? So you can say, I need a cluster with Slurm as my scheduler and X compute nodes that can scale up to Y, right? You can set these parameters and it'll scale up and down the cluster for you as you need. And you can log into the master node, submit jobs as you've always done with, say, at OSC or TAC or NERSC. But throughout the breadth of these services, the goal is to not have like to have parity across them, right? We wanted our customers to be able to use every service with every other service, and we didn't want to build what we call islands of capacity. And I'll get to that in a second. And in areas where we don't really have a native service that suffices for your need, we work with a wide range of partners. This is again a sampling, but we have technology partners with all the CPU vendors. We have application partners, ISVs like ANSYS and all the other heavily used ISV codes in HPC. And we also have consulting partners that extend the capabilities of the native services. These services are not localized to a specific geography. They're across a wide range of data centers spread across 24 what we call geographic regions. So customers can build reliable services spreading across them or pick the one closest to them. And each region also has something called an availability zone, which is a redundant data center within a region, so you can handle failures and disasters and whatnot. And there are 77 of those. And each time I give a talk, I have to go back and check the statistic to make sure the number is correct, because each time the number changes and grows. But having said that, I'm here to talk about networking on AWS. And I want to do that in two ways, right? One, I want to give an overview of how the hypervisor technology has evolved on AWS over the course of, say, the last decade, and how that set us up for building something like EFA. Right, so this is what an EC2 instance looked like back in, say, 2011. I'm showing two abstractions. On the left, I'm showing the hardware abstraction of what we call an instance would look like, and then on the right is the software abstraction. And I picked the CC2 instance type here, which was one of the last instances to use software-based virtualization on AWS. It was a compute optimized Sandy Bridge platform. I think it offered up to 10 gigabits of networking. And if you look at the hardware side of it, you'll see like off-the-shelf Intel 82599 networking adapter, and that was wired up to the hypervisor, which was a typical Xen-based platform. You would have like a DOM0, which is a host, and you would have your guest instances that customers would launch. And the software, the DOM0, if you think about it, right, all the server hardware gets mapped into this management DOM0 layer, and it was the duty of the DOM0 layer to distribute the resources to all the compute instances that would run on that host. And there's a lot involved in getting this architecture right? So it's important to strike the right balance between maximizing the number of cores available to the customer instances and how much you dedicate to actual resources, dedicate to the tasks that the DOM0 would execute, like things like memory and CPU and whatnot. And often if you don't end up getting this right, you end up either oversubscribing the resources and causing jitter in what applications notice, or you undersubscribe them and then you have resources sitting idle again, right? And you still see this architecture used in on-prem virtualization technologies and some of the other cloud vendors, where you would have a certain number of CPU cores or sockets reserved for the virtualization aspects, while the others get used for customer instances. But this was back in 2011. I've skipped a lot of the interim stages, and I'm going to show what things look like today, right? So on the left top, I am showing a little NIC with a nice logo on it. So this was a custom adapter, what we call the Nitro adapter that was developed by one of our subsidiaries called Annapurna Labs. It was an Israel-based company that we acquired a couple of years back. But they built this this smart adapter that's capable of doing DMA operations and taking on a whole lot of responsibilities that a traditional hypervisor would do, right? So we went after what we call the VMM itself, which is in typical virtualization, it's the heart of a hypervisor. And once you remove the expensive device models, you can really re-examine how things work, right? So the first observation we had was, hey, if we can avoid having a general purpose management kind of layer running in software, we can implement all that in hardware. We don't really need to set aside cores, right? And the way we did that was we used a flavor of KVM to build the VMM on that Nitro platform. But we didn't really use, say, QEMU or any of the typical DOM0-like things. So we have no DOM0, we have no host stuff running in software in the customer instance. The other thing we kind of figured out was the DOM0, if you think of virtualization again, you don't really need a management entity kind of running all the time, right? So we did what we call a quiescent hypervisor, which is it only executes when it's prompted to by an instance, right? So a lot of the background tasks that run constantly just went away, and we are able to only invoke the hypervisor when we need it without dedicating resources to it. And in this case, I'm showing a C5N18X large instance type. It's a Skylake platform with 36 hardware CPUs. And if you launch that instance type, you're going to get all the 36 vCPUs and all the memory that's on the instance. So this opens up a lot of interesting possibilities, right? So one thing that it let us do is we now offer what we call metal instance types, which some of our HPC customers really love. Is metal basically means metal. There is nothing between the customer application and the hardware, right? So no virtualization, no nothing. And then customers ask, hey, what about security? So we have additional Nitro chips on the motherboard itself that takes care of management requests, I2C, BMC, SPI, and all that. So this is kind of the final form of the hypervisor revolution, and this sets us up for a lot of cool things. EFA being one of them, which I'll cover in this talk. And the reason why that lets us do EFA is if you see kind of there's a super high representative diagram. It doesn't do justice to what happens under the covers, but the Annapurna adapter or the Nitro adapter that I talked about directly provides multiple functions to the customer instance, whether that's mapping in the NVMe storage devices that we have available, or elastic block storage for your operating system, or enhanced networking with Ethernet and TCP or EFA. And this lets us do OS bypass networking because the Nitro adapter is capable of directly DMAing into user memory. We can support OS bypass networking. And EFA brings another capability, right? So OS bypass networking is just one aspect of it, which helps us reduce jitter in application performance and gives you all the latency benefits of overlapping compute communication and all that. But kind of the key benefit of EFA comes from the protocol that powers it, which is scalable reliable datagrams, which Dr. Panda also touched about a little bit. But before I get to SRD, EFA itself is supported on a wide range of instance types, like I said, compute, storage, accelerated instance types. So this too, there are some new platforms coming soon. But at its core, EFA leverages the existing data center network that we have. So we didn't really, like I was saying earlier, right? We didn't have to build a custom island of capacity with custom hardware just for HPC customers. We were able to use our existing Ethernet-based switching and routing network, which was already capable of handling hundreds of thousands of nodes across all those geographic regions. So we were like, yeah, we have this high bisection bandwidth network that gave us good latency for other use cases, and we have this smart NIC that we have that lets us do OS bypass networking and hardware offloads. How can we combine them together and then build something that'll be useful for the customers? And that's where SRD came in. SRD, and if there's one slide I can kind of summarize the aspects of different key characteristics of SRD, this will be it. So SRD, as the name goes, it's a reliable datagram protocol. So it's kind of inspired by the IBRD semantics as defined in the standard. But why reliability, right? So often we think about scaling, and we know reliability is at odds with tail latencies. So it's hard to drive down tail latency for something like TCP, because TCP, obviously you have the OS involvement, you have things like interrupt handling in Linux, and often the TCP Linux interrupt handling can take tens of milliseconds. And if you add things like interrupt coalescing for performance, that creeps up pretty quick. And TCP is often reactive to network events, right? It cannot predict a lot. So it reacts to congestion, reacts to a lot of things, and quickly if you have packet drops, your retransmission timers can go anywhere up to 50 milliseconds. And if you think of what this does for MPI codes, MPI in a predominant case, you would have your data set kind of split up between different processes in your grid, and different mesh cells are computed on, and then you would have some sort of a ghost cell exchange. And the ghost cell exchange is pretty sensitive to stragglers, right? So if you have, if you're exchanging a vector with your neighbor, and if, let's say, the last packet of your last message is getting blocked, you're bringing down the entire application performance down because of that straggler. So tail latencies are super important to MPI and machine learning as well, but predominant to a lot of the HPC like communication use cases. And if you go back and look at that 10 millisecond number I was mentioning, now if you have a straggler, if the TCP transmit time kind of blows up, you could look at anywhere between like 50 to 60 milliseconds, and that's going to bring the application down to a crawl. So that wasn't ideal. So we still wanted reliability. The second kind of aspect of SRD is the second kind of aspect of SRD is it avoids ordering, right? Meaning it doesn't provide any ordering guarantees. If you think about ordering, you don't really require ordering for a lot of use cases. MPI requires ordering, but that's only for things like tag matching, right? And if you think about, again, like typical application, you're doing large message transfers, and you don't really need to order the entirety of your message that you're sending out. You just need to ensure that you're matching to the right message, you're matching to the right sender, and you can still do that by just ordering enough headers and whatnot, and you don't have to enforce such a strict semantic on your network when you don't really have to, right? So kind of taking ordering out of the picture lets us do a lot of cool things again behind the scenes, both for handling congestion and for how we make effective use of the entire bisection bandwidth available across our data center network. And this is one place where you can be smart or you can be really big, and being really big has a big payoff. And I'll talk about congestion too in a little bit, but I just want to demonstrate what I meant by the whole reliability and failure handling, right? So if you think of two cases here that I'm showing, TCP on the top, SRD in the bottom. TCP, if you have a failure, it's effectively blocked, right? You have head of line blocking. And the recovery happens whenever the routing algorithm, the distributed routing algorithm, converges into selecting a different path for your flow. Otherwise, when two nodes are communicating with a typical data center flow network, TCP would take the exact same static path end to end. But SRD, it doesn't react to events. It constantly gets feedback about the round trip time latencies that gets factored into one of the n number of things that get considered when you pick the right path to use and how to manage the flow. So it's able to react to that much quicker. So you barely notice anything in throughput. Same thing with latencies, right? So it depends on network convergence. But with TCP, when you do converge and when you do come back up, there's a cost you pay to recovery. And that's much less with a protocol like SRD, just because of the ability to react to it. Not react to it, but to be proactive about it. Let's do a time check. Yeah, I have some time. I'll show one last kind of pattern that SRD is designed to handle well, which is Incast. And this is something which is really common in both HPC and machine learning, where like one of the other speakers earlier was saying, in machine learning side, operations like all reduce are pretty common when you're trying to reduce parameters across some machine learning sweep. And also in MPI, you have a whole bunch of collective operations like gather, reduce, and whatnot that often cause an Incast pattern which is a network provider's kind of worst nightmare. But SRD, you'll see on the top, it can across all the flows, right? On the depth axis, I'm showing flows, and on the bandwidth axis, I'm showing the bandwidth of each flow. And it's able to maintain fairness across them. But in the TCP case, even if one flow kind of gets blocked because of head-up line blocking or packet drop, other flows can get greedy and kind of steal the bandwidth, right? So this also causes, in a collective communication pattern, this is going to cause stragglers, and that's not good for tail latency. So really, it's about not just handling the Incast better, it's also about fairness across the flows, both within a customer's job and across customers. So that's it. That's kind of the one-on-one level overview of the hypervisor architecture and SRD. I want to talk a little bit about the software ecosystem and then get into the MPI implementation side after that. So at the bottom, we have the NIC, the Nitro adapter that I talked about. It's supported on a wide range of instance types. Currently, customer instances are limited to a single EFA ENI per instance. That's a 100 gigabit NIC per instance. And the device natively supports 8 kilobyte MTUs, right? And then we have a kernel driver that's part of the RDMA subsystem in the Linux kernel. It's upstreamed, it's available as part of the open source distro flavors. And it exposes 2 queue pair types, right? So the SRD queue pair type, which is a driver specific queue pair type, and it also exposes a kind of a native unreliable datagram queue pair type for customers that do need that. RC itself is not supported, as are none of the other kernel upper level protocols. But there's support for a whole bunch of operating systems, depending on what machine image you want to use. And then RDMA core or libIB words is the interface into the device. So host software and middleware can use that interface to communicate with the device. SRD itself is exposed as a driver queue pair type. Like I said, it's not a standard driver type. This is similar to how some other vendors do custom queue pair types. But there's also a direct verbs functionality if you want to directly interface with the EFA device for any specific operation, whether that's querying specific attributes or creating the custom queue pair type. And then there's the fabric. Again, I can do a separate talk in itself about the different capabilities here, but it exposes the RDM endpoint type to the fabric applications. But in addition to what the device can support, it can optionally add in features. It can optionally support tag matching. It can optionally add in reordering for applications that do require it with ring buffer. It supports one-sided models, FIRMA in the fabric, atomics, the whole set of capabilities I've listed there and more, right? The one thing to call out is if you're on a non-EFA, like an ENA based adapter, a single TCP flow is limited to 10 gigabits per second to enforce some notion of fairness. But because of SRD, we have no flow limit, right? Even if you have a single kind of queue pair or an endpoint from the fabric using EFA, there is no flow limit. So you can get to, you can make use of the bandwidth of the device without hitting any artificial flow limiters. And then I didn't show the entire ecosystem around this, but I just focused on the two MPI and the machine learning side. On the MPI side, all the major MPI implementations have support for EFA. I'll talk about them a little bit. MVAPIC, I've shown it off on the side. I'll explain why. And then we also have Intel MPI and Open MPI. On the machine learning side, we have a Nickel plugin that enables a bunch of machine learning middleware like TensorFlow, MXNet, and so on. Let's see. So coming to MVAPIC, we have a principle or a saying at Amazon that says there's no compression algorithm for experience. And having been in the MVAPIC team and following them after, they were pretty quick in coming out with a version that supports EFA right after we announced it last year. And they already had some experience scaling out MVAPIC UD versions over the unreliable datagram queue pair type. And with some tweaks to that and some custom designs, they were able to directly work on the SRD protocol. Right? So this is a slide that I stole from one of their papers at Hot Eye last year. But if you think of the kind of key designs that MVAPIC has for AWS, one, it directly programs to the RDMA core API. Right? So in the previous slide, I talked about the different layers in the software stack. But instead of programming to the fabric, MVAPIC goes one level lower and directly programs to RDMA core, because clearly of their experience with RDMA core and libIB verbs, and also the gains they've already had with their MAPIX UD design. But by doing that, they also had to implement some of the other things, right? So they had to implement the reordering engine again. So they have a copy out based mechanism that I've shown in the chart there, where if you get a packet that's not what you're expecting, it'll stash it on the side until you get the expected one, and then it'll process it later on in order. And this, like I said, it's important for tag matching, among other things. But to do this, you need some sort of a sequence ID to sequence your packets. So they use the immediate data support for that. And they also extend the 8 kilobyte MPU to support long messages with packetization. And Dr. Panda talked about the advanced features they have with XPMEM that gives you really fast intra-node communication while taking a dependency on the XPMEM module. And again, I've seen some early numbers. Dr. Panda presented some numbers with their release, and they're looking really good. Right? They're able to exploit the native capabilities of the device pretty well with their designs. And this is a space I would watch out for. We're collaborating with them. We're doing a lot more things. So really excited for what we can do here. I have just 5 more minutes. Let me skim through the rest. And I don't want to get into the details of the other implementations here because it's the MAPIX user group meeting, and I don't know how much interest people will have. I just wanted to show like one slide each. So with OpenMPI, again, there are multiple conduits that let you run the OpenMPI on different networks. So for EFA and SRD, we use the OFI MTL, which is the Fabric MTL path. And depending on what version you're running, there's also a BTL component for certain code paths, right? For things like RMA and atomics, it goes through the OFI BTL. Again, Intel MPI also announced support for EFA starting version, I think 2019 update 6. It's a similar kind of layer cake diagram where it uses the CH4 abstraction and uses the OFI transport layer. And Intel MPI supports a whole bunch of the fabric providers, so they don't really have to make any changes to use the EFA, the fabric provider. And here too, we've been working with the Intel MPI team to constantly evolve this design and have better support for it. And I showed a lot of layer boxes. So to make it easy on our customers and users, we make an installer package available that gets you the kernel driver, the right configurations for different system settings, the RDMA core stack, and so on and so forth. So you get a tarball, run it, and you have everything that you need. So I'm going to kind of skim through some performance results that I have. This is somewhat of an outdated chart. I didn't have time to update it, but on the left, I'm showing multi-stream bandwidth that you can get with different compute instance types on AWS, C3 being a really old generation, and I'm showing multi-stream bandwidth across generations leading up to the green line, which is the ENA bandwidth you would get on a C5N 100 gigabit instance type, and then of course EFA. And you can see EFA obviously exporting all the bandwidth available to the system and gets over to like 93-ish gigabits per second. And on the right, I'm showing latency across the compute instance platforms. This is something we're constantly iterating on and improving, right? So one big area where we're continuing to shave latency as much as we can and bring it closer to the hardware. But micro benchmarks are one thing. And what's really interesting is to talk about customer use cases and real application scaling. This again, we've been working with the MAPIX group. We'll soon have some results there with real applications. I forget if you already showed some numbers or not, but these numbers are not with the MAPIX. So I have a mosaic of results with different implementations, but really demonstrate the impact of SRD. This is with ANSYS Fluent. I'm a huge Formula One fan, so in most of my talks, you'll see results with Formula One cars and how they use HPC. So I'm both a HPC and a Formula One geek. But this is with ANSYS Fluent, which is a heavily used code, not just on AWS, but also on-prem. And this, we worked with a partner. We were able to compare some data we got on XC50 with the AWS C5Ns using EFA up to 7,200 cores. And the scaling looked pretty good with the data set that we had with 140 million mesh cells. This is another CFD app. This was with a partner called Xenotech. And this is to demonstrate EFA with the GPU instance type. And this is measuring the iterations per minute, the throughput that you can get with this particular the ZCFD workload. And this was comparing it with CS500, our own CPU instance type. and a whole bunch of our GPU instance platforms. The P3 series use the Tesla V100 GPUs. The G4 series use T4 GPUs. And they did some math with the cost, and they were able to get better through scaling and throughput for iterations they could churn out with the lower cost. So that was pretty exciting. And then one other Formula One case study, and I promise this will be the last one. So this is work that the Formula One, the organizing body itself, did with AWS. Not each of the teams, but they were trying to simulate the wake generated. So if you have two cars following each other, kind of going at it, and the wake of the first car's aerodynamic impact is going to affect the car behind it, and that's a safety concern, right? So Formula One kind of defines the specifications and standards around how you can design your wings so you don't pose the person behind you at risk. And they were doing this for the 2021 season, and they were able to bring down their simulation time using the EFA and SRD stack from 60 hours to 10 hours. That was super exciting, and they were really happy about that. And then let me see time. I have like 30 seconds, so I'll skim through this chart. Again, this is a study one of our customers did. This is the Naval Research Lab, and their goal, this is a weather app, right, NAVGEM, and their goal is to simulate a day's worth of forecast in 7.5 minutes. That was their target, right? And they were trying to evaluate a whole bunch of solutions out there to see which one worked best for them. The horizontal line that I'm showing somewhere in the bottom third is the mark for 7.5 minutes, right? So this was a 19-kilometer use case, and they were able to, in some other case, like with DSRC, their own on-prem system, they were hitting it with 500 cores. EFA, like the red line, is able to scale up through 1,000 cores, and then you start seeing that step variability towards 1,000 cores. I recommend that talk. It's a pretty interesting talk to watch, even outside EFA. They can talk through how they think about weather modeling and why it's important to generate that forecast in that time. So highly recommend that talk. And yeah, that was it. I kind of breezed through a lot of content, but before I close, I want to say thank you to the MapRich team. Like I said, they've been on top of new technologies that come out, and they were one of the first ones to add support for SRD. And I'm really excited to see what's coming next.
Raghu, thanks. There are a few questions in the Q&A box. If you can open up,
sure. Let me try that. All right, I'm looking at Adam Moody's question.
There are 3 questions. Yeah.
Yeah.
Right.
We say that's already something. Yeah. Hey, Adam. Long time. Yeah. So
can you also repeat the question?
Sure.
Because some people cannot see that. Yeah.
Sure. Adam's question was: did you say that SRD is sending each packet multiple times through the different routes and parallel to account for lost packets? If not, go to end. Okay. So no, that's not happening. So what we do is we use our existing, like we already have a vast, like I said, a huge bisection bandwidth network with Ethernet switches and routing. We use the ECMP flows in our existing infrastructure to route packets. So each flow kind of picks a path dynamically based on the congestion in the network and uses that, right? And the sender doesn't know for the lifetime of the transmission with a peer what route it's going to take, right? That changes. But instead of using a static path, it just takes a different path. It's not redundantly sent across multiple paths. That made sense. EFA is said to be RDMA-like. Can I confirm whether EFA is true RDMA? So RDMA and OS bypass are two separate things, right? So EFA, the device, is capable of OS bypass networking, and it has all the capabilities needed to support true RDMA, but we do not support it yet, right? Then Pavel Shamis asks how SRD performance compares to WebS UD in terms of latency and bandwidth. What is the packet drop rate for UD? What are the other features can be found in SRD and are not present in UD? Thanks. Yeah. So I think I could be wrong, but one of Dr. Panda's papers had some results comparing MapRich over UD and MapRich over SRD. I think that's also in the Hot Eye talk. Is that correct?
Yeah. In fact, I presented that in today's morning talks also.
Yeah.
The MapRich to number with SRD and UD.
Right. And the other feature is, so SRD lets us do, because we built it on our Nitro platform, I kind of, the metaphor I like to use is like buying a Tesla, right? You buy a Tesla and then tomorrow it learns how to drive itself. So because it was a software-based implementation, we could add features to it as we go with what we call live updates. We can roll out features to our customers without even them realizing it. So this is something we're constantly iterating on. So in the fullness of time, you'll see more and more features coming down the road without having to upgrade your infrastructure. But I think that's my time. If you have any questions, I'll stick around both in Zoom and Slack. So feel free to